Okay, in this video we're going to learn how to simplify expressions wherein we have to multiply radicals, such as, for example, 3 roots of 2 times 5 roots of 6. We've talked about how to add and subtract them. Now we're going to talk about how to multiply them. So let's do that first example. So we're doing 3 roots of 2 times 5 roots of 6. And we know that if I have 3 roots of 2, we should know that that's really just 3 times the root of 2. And then I can bring down my times. And 5 roots of 6 is really 5 times the square root of 6. Whenever we have those numbers that are basically like coefficients, it's just 3 times that value with the radical. So I could rewrite this with just a whole bunch of multiplication. And then we know because the order doesn't matter when we do multiplication, we can reorder these. So I'm going to reorder them and do 3 times 5 times root 2 times root 6. 3 times 5 gives me 15. Root 2 times root 6, well, when I'm multiplying values that are in radicals, I basically multiply those radicands, and that becomes 15 roots of 12. Now, you would think that we're done, but I do want to kind of keep us in this mindset. Anytime you do something where you simplify radicals, we need to stop and check our radicand and see if we can simplify our radicand. I know that the root of 12 is probably not the simplest form of that, so I'm going to keep my 15 and I want to break 12 down into its prime factor. So I can first go 3 and 4, and then I know that can become, the 4 can be 2 times 2, and anything there's 2 of, I can basically put one of those out front, and so my coefficient will become a 30 because 2 times 15 is 30. And then I'm left with the square root of 3. So basically, to kind of summarize, what I do in problems like this is I'm going to multiply the coefficients, and here I got 15, multiply the radicands, here I got 12, and then whenever you're done, just make sure you can't simplify your radicand a little bit further. But our final answer to that one would be 30 roots of 3. Okay, here's the first example that we are going to do. And so really the parentheses here are just to show multiplication. So I can rewrite this without parentheses if I want to. These are all times symbols. I don't want you to think those are minuses. And then as we learned in the last slide, I can multiply my coefficients, which would be negative 5 halves or negative 2.5. And then I could multiply my radicands, which would be the root of 50. Then, just like the last problem, we need to stop and see if the root of 50 will simplify. So I'm going to bring down my 5 halves, and I know 50 is 10 times 5, and I know 5 is prime, so it's done, but the 10 can be broken down a little bit further. So I have 5 roots of 2 times, and the 10 can become 2 times 5, and then I bring down my other 5. Anything there's 2 of, I'm going to put 1 out front. And so now all that's left in my radicand is the root of 2, and then whenever I multiply these, that's going to be negative 25 halves, or in other words, what is that, negative 12.5 roots of 2 if I went to a decimal. Now, this part I didn't really talk about on the last slide. I'm kind of hoping we're getting to the point where we can multiply fractions, but if you are wondering how I got from there to there, just know that to do a whole number times a fraction, you can just put that whole number over 1 and then multiply straight across. 5 times negative 5 is negative 25. 1 times 2 is 2. And if I were to just divide that in the calculator, that's how I got that negative 12.5. That is my final coefficient. But that would be my final answer right there. Let's do another one. Now, here we just got to think order of operations. I think if I were to write this a little bit differently, we'd know exactly what to do. Like, for example, if I was dealing with this problem, we would know exactly what to do. You say, oh, I just distribute that x into my parentheses. Well, the only difference between this and this is that I've replaced the x with the root of 5. Okay? So I hope we see the similarities here. And since we would distribute an x in this situation, we're going to distribute a root of 5 in this situation. So if I start by distributing that root of 5, 4 times the root of 5 is just 4 roots of 5. Be careful, this is not the root of 20 because the 4 is not under the radical. We're multiplying a whole number times a radical, so the 4 is kind of like a coefficient that's going to go out front. We have 4 of this value because we're multiplying it by 4. And same thing here. If I do root 5 times 3 root 5, that's going to be 3 root 25. Now, if you were kind of confused at that number, if you're saying, oh, how'd you get that? I can kind of come over here and show you some aside work that is how I got it. So we basically just did root 5 times 3 root 5. But what we got to remember is just like if this was just an x, it's the same thing as 1x. So I could have that 1 coefficient right there. So if I did it that way, I would have 1 times 3, which would be 3. And then I'd have root 5 times root 5, and I multiply my radicands to get the root of 25. So that's kind of how I got this number right here. So I guess I can leave that there. Now that we're here, we're still not quite done. We have a value that can be simplified. The root of 5 is prime, so this term can't be simplified any further. But this one actually can, because the root of 25, that's actually a perfect square. So if I have 4 roots of 5 plus 3 times the root of 25, we should know the root of 25 is just a 5. And so this is really 4 roots of 5 plus 15. And then you'd have to stop at this point. In our adding and subtracting radicals lesson, we learned that I can't add terms together unless they're like terms, meaning this would have to be 15 roots of 5. There would have to be a radical on this term as well for these two terms to be like. So since we have a term with a radical and a constant, those cannot be added, so we're just done with 4 roots of 5 plus 15. Here is our last example. And so once again, we might think that I can just take that exponent and stick it onto both, but I want to kind of draw our attention back to what we did a long time ago with this. If I had like 2x plus 7 squared, we spent a lot of time a few units ago emphasizing how that's 2x plus 7 times 2x plus 7, and then we got to do all of our distribution. Basically, if I have a binomial, notice it's a binomial because there's two different terms squared. I have to write that out as that value times itself and work it out that way. So that's exactly what we're going to do here. Even though this is not an x, it's a radical. It's still the same idea. These same rules that we've learned for multiplying binomials are still going to hold true. So we have this times itself. So that's going to be 2 roots of 5 plus 7 times 2 roots of 5 plus 7. And so I'm going to multiply it like that. So first I have, hopefully, I'm going to expand it out. I hope this doesn't look confusing to you. But basically, I'm going to start with 2 roots of 5 times 2 roots of 5, which is this first distribution, okay? And then I'm going to add that to 2 roots of 5 times 7. And then I'm going to add that to another 2 roots of 5 times 7. And then lastly, I'm going to multiply my last terms and do 7 times 7, which is 49. So I kind of wrote a very expanded version, so I hope this doesn't confuse you, but I think it's going to help us to look at these as 4 little individual multiplication problems. So first off, 2 roots of 5 times 2 roots of 5, what I got by distributing this first term into the first term there, as we've established, I'm going to multiply the coefficients. 2 times 2 is 4, and I'm going to multiply the radicands. 5 times 5 is 25. So that's that. And then plus, bring down my plus sign, 2 roots of 5 times 7. I gotta be careful. I can't multiply the 7 times the 5 because the 7's not under a radical. I have 2 roots of 5 times 7. So I'm going to multiply the coefficients, 14 roots of 5. I just multiplied the 2 and the 7. And we see that this is actually the same right there. So that's going to be another 14 roots of 5. And then lastly, I can bring down my plus 49. Now, let's keep going. 4 roots of 25. We've already seen a root of 25. 25 is a perfect square. That's just 4 times 5 because the root of 25 is just a big 5. And then what we got here is we have some like terms. I have 14 roots of 5 plus 14 roots of 5. Because they have the same radicand, they both have that root of 5, we can add those together. So if you have 14 of something and you add 14 more of that something, you end up with 28 of that something. So I just basically took those two middle terms and combined them, and then you have your last constant over here. So 4 times 5 is 20, plus 28 roots of 5, plus 49, and then my last step is I've got some like terms combined. We have two different constants, so that could be written as 20 plus 49 would be 69 plus 28 roots of 5. I would always warn you to make sure your radical doesn't simplify at the end of the problem. Since we have a root of 5 here and 5 is already prime, I know that radical is not going to simplify. So there we are, done, the end.